So here's a little bit of information on polynomial functions. So the previous section looked at a power function. And a power function takes on the property of y equals a constant times x to some power, where the power could be positive or negative. It could be a whole number, could be a fraction, just some power, like a rational sort of power. So whenever we look at polynomials, again, a power function is one single term. For polynomial functions, that is going to take a sum of power functions. Could be 2, could be 3, could be 7. But it's going to take a bunch of power functions whose exponents are very particular. The exponents are non-negative integers. So in other words, those are going to be your positive counting numbers. Okay? So while power functions can have other powers, when they get put in a polynomial added with positive or negative coefficients, they're only going to be those positive counting numbers as far as for the polynomial. So, and some examples are, x cubed plus 2x squared minus 8x plus 11. Or maybe it'll be the polynomial 5 minus 2x plus 8x to the 5th. So all of those different power functions that are being added together, those are called terms. Okay, so like the top one has 4 terms. The second example has 3 terms, and it's just how many of those power functions get added together. You'll be asked to identify the degree of the polynomial, and the degree of the polynomial will essentially just be based on whichever power is the highest, based on the term. So wherever the highest power or exponent lives, that will determine what the degree is. So the example from above, the x cubed plus 2x squared minus 8x plus 11, the cubed power is the highest degree on any of the terms. So the degree of this polynomial is 3. The fact that that x cubed term has the highest degree, there's another phrase that you need to know called the leading term. And the leading term is going to be whichever term has that highest power. So whichever term has that highest power, it's that whole entire term. So in this case, the one x cubed. Okay. So then we have the degree you have to pick out. You have to be able to identify the leading term. You might also be asked how many terms it has. So like for this example, if it says how many terms does it have, there's 4, right? We got 1, 2, 3, 4. So the degree, the leading term, the number of terms. So here's another example. Say it were 5x to the 4th minus 3x to the 5th plus 8x squared minus 12x plus 3. Okay, it's a little bit longer of a polynomial, but still a polynomial. In this case, the terms are not necessarily given in descending order or ascending order, and so you may have to search through the polynomial to actually pick out the leading term and what the degree is. So in this case, this negative 3x to the 5th is going to determine our degree. That's where the highest power lives, power of 5, so the degree is 5. The leading term, make sure you pull that negative, and it's negative 3x to the 5th. The negative 3 is called a coefficient on that term. The number of terms here would be 1, 2, 3, 4, 5. There's 5 terms here. So being able to identify the degree, the leading term, how many terms there are, those are things that you need to know how to do with polynomials. The other thing that you're going to have to be able to do is to describe the long run behavior. And the long run behavior is really just what the function does at the ends. Like, what does it do when x gets really large? What does it do when x gets infinitely large? But the long run behavior is going to be based off of the behavior of that leading term. So whatever that leading term is will tell you what it does. And we've seen before, if the polynomial has an even power, then it'll have one of those shapes where you don't really know how many squiggles it might have depending on how high the power goes. But at the ends, so it's this piece in the middle that we're not really sure what happens. So we're not exactly, who knows? We'll learn about more of that in the next section. But it's end behavior as x gets really large in the infinite sense or really large in the negative sense. If the ends are pointing upward, the long run behavior here of the function actually goes up to positive infinity, whether x gets infinitely big or as x gets infinitely big in the negative sense. The end behavior or the long run behavior, if it's an even degreed polynomial and it points up, the long run behavior will go to positive infinity. If it's an even power and that coefficient happens to be negative on that leading term, that'll have the same shape, but now the ends are going to be pointing down. And again, you don't really know the kind of humps that it may have, and turns that it may have. But the main focus here is that the ends will go in the same direction. And if it's a negative coefficient with an even degreed polynomial, the long run behavior of the function will go to negative infinity. Whether x goes to positive infinity, gets really large in the positive sense, or x gets really large in the negative sense, the function behavior for that shape where it points down is negative infinity. Whenever you have an even power, an odd power, depending on, like to the third, to the fifth, to the seventh, if there's a positive coefficient on that leading term, then it'll take, the shape where the ends go in opposite directions. And it may have some humps, changing the concavity. It may have a few of them. But the thing that's going to happen is that the ends go in opposite directions. And if it's a positive coefficient, whenever s gets really large, the function value will go to infinity. However, as x gets infinitely small, in the negative sense, not infinitely small to 0, but infinite to negative infinity, then the function values actually point down to negative infinity. So there is your long run or end term or the long run behavior for that kind of function. If you have x to an odd power and you have a negative coefficient, it's just going to flip it. It's going to make it go the other direction. And again, it may just depend on the power, how many zeros it has, what the function actually does. But you have that end behavior going in opposite directions, and as x gets infinitely large, the function value actually gets infinitely large in the negative sense. And then as x gets infinitely large in the negative sense, the function value actually goes up to positive infinity. So those are the long run behaviors for your, depending on whatever the leading term is. Again, we'll focus more on what happens here in the middle with the humps and the turns and the concavities and all those things and the zeros. But for the long run behavior, you should be able to look at the power, look at the coefficient, determine which direction it goes, and be able to describe the long run behavior.